All right, so now we're going to look at what are called monotone equations and the idea of algebraic stability. Okay. So we had seen previously it's like this idea of astability, right? So let's see. So recall we discussed sort of astable methods. And one way of thinking about astable methods is that which sort of correctly capture the dynamical properties of sort of linear ODEs. Y prime is A of Y, right? When all the eigenvalues of A reside in the left half plane. Okay. All right. Okay, so now we're going to look at something similar to this concept, or sort of analogous to this concept, but in a nonlinear setting. Okay, so we're going to generalize to a nonlinear setting. Okay, so let's set this up. So let's say that you have an inner product denoted by these angular brackets. And this is an inner product in sort of D copies of complexes. And there's a induced norm, right, associated with this inner product. So what I basically mean by that, of course, is that if you take the norm of some thing, this is equal to the inner product of that with itself, and then you take the square root of it. Okay, all right, so that's what we mean by the induce, the norm which is induced by the inner product. Okay, and then we say that a differential equation let's say y prime is f of t and y, right, for t greater than or equal to 0 is monotone. Right, and it's always with respect to the given inner product. If f satisfies the following, okay, that the real part of the inner product of the difference between u and v and f evaluated at u and f evaluated at v, right, is less than or equal to 0. And this is for t greater than or equal to 0 and for u and v, which are in the complexes. CD. Okay. All right. So you might ask, it's like, what's the significance of this inequality, and more or less it's like what we're going to show is that if the differential equation or the vector field satisfies it's like this kind of relationship, then the norm, it's like of the difference between u and v, right, is monotonically decreasing, right, or monotonically non-increasing. So let's try to prove that, right? So let me state the result and then we'll try to prove that. Okay. So let me first state the lemma. Okay. All right. So right. So if y prime is f of ty, right, satisfies the sort of monotonicity condition, star, right, the ODE is dissipative. Okay, in the following sense, right? So given two solutions, u and v, say with different initial conditions, right? Well, of course with different initial conditions, right? With u at 0 is u0 and v at 0 is v0. The function right, which measures the distance, it's like between the two solutions at a given time, right, decreases monotonically. For t greater than or equal to 0. Okay. All right. So let me try to erase everything except the inequality and prove this result. Okay. So you have phi of t, which is 1/2. It's like the square of this distance. Right. So of course this is nothing more than 1/2 u minus v, right? Which is of course just a definition. It's like of how the norm is related to the inner product if it's the induced norm. Okay, all right, it's the associated norm. Okay, so if we can differentiate, it's like this function. So this is just 1/2 the time derivative of this inner product, u minus v, u minus v. Okay, and all right, so this is just 1/2 u prime minus v prime, u minus v, plus u minus v, u prime minus v prime. Okay, so I should say that these u's and v's, it's like all depend on time, so I'm just suppressing them. It's like for notational simplicity. All right, but of course u prime minus v prime is just this thing here. Okay, so it's 1/2 f of tu minus f of tv, comma u minus v. Okay, and then of course it's like the inner product, right, is you can sort of collect these two things. So this is just u of t minus v of t, f of t u minus f of t v, right? And then there's this inequality here, which is less than or equal to 0. Okay? All right. Okay, so that proves the lemma that the rate of change in cycle of this distance is decreasing, right? Or it's not increasing, if you will. So essentially, it's like one way to think about this lemma. What this lemma is basically saying is that if you have two different solution trajectories, then they will start, well, they don't necessarily approach each other, but they never sort of grow further apart from each other. Okay? And the implication of this is that if you have if these two represent perturbations of each other, maybe with slightly different initial conditions, then those perturbations remain small forever. So in particular, this implies that small perturbations sort of remain small, right? So there's some sort of stability-like condition here. Okay, so that's this idea of monotone equations. Then the next obvious thing to ask is under what conditions on your differential, well, on the numerical method, are guaranteed that when you discretize a monotone equation with that numerical method, the sort of discrete time analog of this monotonicity condition is satisfied. Okay, so let me just stop here for a minute. In a second, we'll get back to discussion how to construct numerical methods which preserve this property.